Welcome to the second part of Lecture 2. In the first part of this lecture, we talked about binary numbers, how they can be represented in a computer using transistors, and even simple arithmetic like addition and subtraction. The kind of reasoning we used for performing addition and subtraction on binary numbers was based on an algebra we had earlier learned at school, which is called elementary algebra. In elementary algebra, values of variables are numerical and basic operations are addition, multiplication, etc. But this is not the kind of algebra that a computer understands. What computer understands is Boolean algebra, which is a branch of algebra in which the values of variables are not anymore numerical, but they are Boolean values. Boolean values are true and false. They can also be shown by 1 for true and 0 for false. And the basic operations here are not anymore addition, etc. They are rather not, and, or. In the rest of this lecture, I'm going to talk about these operations and how they are implemented inside a computer. Besides basic operations, we have secondary operations such as XOR, NAND, NOR, etc. I'm going to discuss about their implementation and their use as well. And why do we need to learn about Boolean algebra? Because this is very fundamental in development of digital electronics that we are going to use every day. And digital circuits are actually based on Boolean algebra. And even in programming, it happens often that we need to use Boolean algebra. A logic gate is a building block of Boolean algebra. A logic gate basically implements a Boolean operation such as AND, OR, XOR, etc. These logic gates make digital systems possible. Each logic gate, as we will see in the coming slides, has a logic symbol, which is used universally to identify the gate. And inside the logic gate, there are actually one or more transistors that build that gate. So let's review what a transistor is. Transistor is a semiconductor device that can have two rules. It can either switch or amplify electronic signals. In this course, we just talk about the role of transistors as a switch. When a transistor acts as a switch, it can be on or off. Transistors are the basic building block of all digital circuits. Nowadays, the CPUs have like millions of transistors inside. A transistor has at least 3 terminals that's connected to the external circuit. This is usually the graphical symbol used to show a transistor, and it lists all its 3 terminals. This terminal here is called the base, which acts as a controller of the transistor. This other terminal is the collector, which is basically the input to the transistor, and emitter is the output of a transistor. You can think of transistors as faucets or water taps. When base is turned on, it's like opening the water tap. So it lets the electricity flow through the transistor from the collector to emitter. But when base is set to off or is 0, then no electricity will flow through the transistor. But let's see how transistors are used to build logic gates. The primary logic gate that we need to introduce is called buffer gate. Buffer gate, as you see, has a logic symbol, which consists of a triangle, which is pointing towards the right, and it has an input here. Here, the input I chose to be only 1 bit, and it has an output of 1 bit. And a buffer is very simple. Its output is exactly the same as its input. So the inputs and outputs of all gates and later on the circuits that we will see can be summarized using something called the truth table. So here you see we have the list of all possible inputs and their corresponding outputs. A buffer gate, which is a logic gate, can be implemented using one transistor like this. There are different ways that any logic gate can be implemented. I just want to give you an idea of how they are built using transistors. You don't need to remember all the details. So here we have a transistor. Its input is connected to a source of electricity, and its controller is connected to a resistor, and its output or emitter is actually the output of the circuit, and it's also connected here to a resistor. So it works like this. If the transistor is turned on by giving the input a higher voltage than 0, then the electricity is allowed to flow through the transistor. So the output will also be 1. But if the transistor is set to off, the electricity is not allowed to flow here, so the output will be off. So the input and output are the same for buffer. It doesn't seem very interesting because its input and output are the same, but it is actually used in logical systems for computations. So a truth table is a mathematical table used in Boolean algebra. As I said, it lists all the outputs that correspond to all possible inputs. Because the example we saw had just a very simple input. It consisted of only one bit. But we can have many bits of input to our circuit or to our logic gate or logic circuit. So it is very important that we know the truth table, which summarizes all the information about the circuit for us. We will see this in the coming slides. Here I want to introduce you to a tool which is very useful for simulating and building circuits. One way to build circuits is that you buy the gates and transistors and wire and connect them together to build your circuit, but you can actually simulate your circuit using different software. Logisim is one of the very practical ones for educational purposes. So I will show you in the rest of this presentation how we can use it. So the next gate that I want to introduce here performs the operation NOT. As you see, its logic symbol has like the symbol of buffer plus a circle. Circle here shows the negation. The output of a NOT gate is the complementary of its input. So if we take a look at its truth table, we see that whenever output is at logical 1, the input is at logical 1, then the output is at logical 0. These ones and zeros are the truth values. They are not like 1 and 0 in decimal. We treat them differently in Boolean logic. And when input is 0, you see that output is 1. And its implementation can be like this using a transistor. So this time we have a transistor, which is like the previous time connected from its base to a resistor, but then its input now is connected to the electricity source by a resistor. And the output is just before the input to the transistor. So what happens is that when the base of a transistor is turned to on, we will have a short circuit. And it doesn't let the electricity flow through here, so the output will be 0. But whenever the transistor is set to off, then the electricity will be able to flow through here to the ground, so the output will be 1. So the output, as you see, is the inverse of the input. Let's try this with Logisim. So here in Logisim, we have the list of gates here to the left that we can choose from. So here I pick a NOT gate, and you see each gate has an input and an output. So as input, I pick this. I need to connect it. I drag from the input to the output, to the gate to connect it. And I also need an output. So I select an output and drag it here. You see input and output have different symbols. And now I can try this circuit. This is a very simple circuit, just consisting of an NOT gate. So I choose the hand tool to turn it on and off. When I turn it on, the output you see is off, it is 0. When I turn it off, the output is 1. So it's the complementary of input. And when we want to write it, the Boolean expression will be like this. So here the output y is equal to a bar. Bar is used in Boolean expressions to show negation. The next gate I want to talk about is AND gate. AND gate implements the AND operation in Boolean algebra. And it works like this. Its output, you see here, you have this output and these inputs. Its output is at logic 1 only if all its inputs are at logic 1. It might seem difficult, but it's like it's very simple. We use this kind of logic every day. For example, if I say I am giving a lecture and I am sitting, this expression only holds if both parts hold at the same time. This is this similar principle here. So the output holds if all its inputs hold or are at logic 1. Here I have shown only 2 bits of input, but they can be more. And to the left, you see its truth table. The truth table, as we said, needs to list all possible input variables. Here we have 2 bits of input. With 2 bits, we will have 4 different cases because we are in binary. So we can have 0, 0, 0, 1, 1, 0, and 1, 1. These are all possible cases. And for these inputs, we need to write the corresponding output. In this case, we said that for AND gate, the output is 1 only if all inputs are 1. So you see that in other cases, the output is 0. And its implementation with transistors is very interesting. We need to use 2 transistors when we want an AND gate with 2 bits of input. Each transistor is connected to one of our inputs, and the output from the first transistor will be the input to the second one. And the output of the second transistor is actually the output of the circuit. And you see that this output will only be 1 when both of these are 1. Because when the first one is 1, the electricity can flow from the source to the second one. And when the second one is on, remember the transistor acts like a water tap. So when its base is 1, it will let this flow continue and reach here, which is our output. The next basic gate is OR gate, which implements the OR operation in Boolean algebra. The output of a OR gate is at logic 1 when at least one of its inputs is 1. Consider this expression. I say, I am giving a lecture or I am eating. Although I'm not eating, but since just one of my expressions is correct, this whole expression is correct. This is the same concept here. So you see that the output is 1 when at least one of the inputs is 1. And its symbol its logic symbol is like this, and its Boolean expression is written as A plus B. Although the character plus is used here, but it is not the same plus as we have in elementary algebra. It's a whole different thing, because 1 plus 1 here will not be 2. It will rather be 1, because we have logic 1, not a decimal 1. And its implementation with transistors is that you see here. So again, we need 2 transistors, but both of their outputs are connected to the output of the circuit. So if any of these transistors is on, then the electricity will flow from the source to the output. And if just one of them is on, it is enough for the output to be true. Otherwise, the output will be false or 0. Let's see how we can use AND and OR gates in Logic. So we have AND gate here, for example, and OR gate. For each gate, we can decide the number of inputs in terms of bits. So here I choose it to be 2, for example. So I need 2 of these inputs because each of them I have picked the default, which is 1 bit. And I connect from this input to this port, and from this input to here. And I need an output as well. And I connect it to the output of the gate, and I try it with the hand tool. So when just one of the inputs is 1, the output of the gate is 0, and it is only 1 when both of them are 1. I can try OR gate as well. So here again, I pick 2 inputs, each of them being just 1 bit, and I connect them. And I also connect it to the output, and I try it. So here I set the input to 1, you see the output is 1. When I set the other one to 1, again the output is 1. And I can see also the truth table for my circuit. Let me delete this part. So when we go to project, analyze circuit, we see that the inputs are listed and the output is listed, and we see the truth table. So it's similar to what we had inside the lecture. Now let's go back. So now we have covered our primary operations in Boolean algebra being AND or not. Now let's take a look at the secondary operations. One of them is called NOR. It is actually the negation of OR. And as you see in its logic symbol, we have the symbol that was used for OR, followed by a circle. Circle shows negation in logic symbols. The output of this gate is at logic 1 when all the inputs are at logic 0. So you see it is opposite to the OR gate. OR gate was 1 in all these 3 cases, but here we have the opposite. So it is 1 when all the inputs are 0. And its implementation using transistors is similar to the OR gate, just that the output becomes before the transistors. The next gate is NAND gate, which stands for not AND gate. So as you see here in its symbol, it has the symbol used for AND gate plus a circle, which, as I said, shows negation. So as you expect, the output of this gate is at logic 1 when at least one of the inputs is at logic 0. So it is as opposed to the AND gate. So in the AND gate, only at the last row, the output was 1, but here is the opposite. So in all the cases where at least one of the inputs is 0, the output is 1. And its implementation using transistors is the same as implementation of AND, just that the output and the resistor connected to it should come before the first transistor. For any of these gates, we can have more bits, but the same logic applies, meaning that even if, for example, we have 16 bits of input, we will have just 1 bit of output, and this output will be at logic 1 when at least one of the inputs is at logic 0. But the truth table in that case will be much bigger. For example, if we have 4 bits of input, we will have 2 to the 4 different cases, 16 different rows in our truth table. The next gate, which is used very often, is called XOR gate. In XOR gate, the output is at logic 1 when one and only one of the inputs is at logic 1. So you see here, it's a bit special. So the output is 1 when just one of the outputs, inputs is 1. When both of them are 1, the output is 0. When both of them are 0, again, the output is 0. And you see here, I didn't bring the implementation using transistors. I thought it is interesting to see its implementation using other gates. So as you see here, XOR can be implemented using 2 NOT gates, 2 AND gates, and an OR gate. So let's try this simple circuit in Logisim. So as we saw, we need 2 NOT gates, 2 AND gates, and then OR gate. And we need 2 bits of input. I want to give them names, so I click on it and come here and change its label. Another input being B. And I connect from A, drag to the NOT gate, and I connect the output of the NOT gate, the AND gate. I can limit the number of input bits to my gates, but if I don't connect anything to them, they will just be excluded from the computations. And I want to also connect A to this second AND gate. And I need to connect B to this NOT gate and connect its output to the AND gate. I also need to connect B to this first AND gate. So although you see these wires are kind of overlapping, but they are not connected. They are just crossing each other. And what else? I need to connect the output of this first AND gate to the OR gate. And I need to connect its output here. And I need an output. And I connect from the output of the circuit to this output port. Now let's try the circuit. So now both inputs are 0, the output is 0. Let's use the hand tool to turn on A. You see the output is 1. When I turn on B, the output will be 0 because as you saw in the slide, when both of them are 1, the output is 0. And when just B is on, the output is 1. And we can see its truth table. So we go to Project, Analyze Circuit. So you see that our inputs are listed as we have A and B. And the output, we didn't give it a label, so it has a default label. And its truth table is as we expected. So many different circuits, anything you can imagine, can be simulated here in Logisim. And this is a summary of the gates we saw. So buffer gate has this logic symbol and it's this truth table, and it is written simply by output is equal to input, which in this case is A. And for negation, we saw we used the bar. For and, we used dot. For or, we used plus. And this is the symbol used for XOR. So this is A XOR B. And here NOR was actually the negation of OR. So we have the bar on top of plus, because plus was OR. So logic circuits, as we saw already in our small examples in Logisim, are built using logic gates. You remember in doing arithmetic operations on binary numbers, we simply use the kind of logic we had learned at the school to do addition and subtraction. But when it comes to computers, they need to implement it using logic circuits. For example, this circuit you see to the right actually implements the sum of 2 bits. So here we have 2 bits, A and B. Actually, so each of them is just 1 bit. And we sum them up together, and we have a carry bit. In the beginning of an addition, the carry is always 0, but in the next bits, as we saw earlier, in the first part of the lecture, it can be 1. And you see how many gates are put together to just implement this simple operation. We have 2 XOR gates, 2 AND gates, and OR gate. And this is the result of the sum, and this is the carry of the sum. So this will be used in the next bit if you want to add up more bits together. So imagine in current computers that we are using, our machines are usually have data which is as big as 32 bits or 64 bits. So then if we want to just add 2 numbers which are 64 bits, we need to have 64 such adders, because each of them is just simply adding 1 bit of data from the first input to the 1 bit of data from the second input. But these circuits are in reality nowadays very small inside our computers, so that like millions of them exist in our CPU. I have added an optional assignment that you can do in Logisim, and I have added instructions so that you can implement simulate a simple circuit in Logisim. So now that we have seen how binary data can be represented in computer and how Boolean algebra can be performed in computer using logic circuits, we should also talk a little bit about how data can move inside the computer. Because imagine this is the memory that stores the data in our computer, and this is our CPU that wants to do these Boolean algebra operations. They need to connect in some way so that data can move from memory to CPU, so that on the data the operations are performed. How is this movement done? So inside the computer, buses are used for moving data around. Bus is simply a group of electrical wires that carry a signal. And buses have different speeds. The speed of a bus is measured in megahertz, which is a metric for measuring frequency. And the speed of a bus determines how much data can be carried on the bus simultaneously. And we have also the notion of size of a bus or width of a bus, which shows how many bits of data can a bus transfer at the same time. So usually nowadays computers have buses which are as long as 64 bits. We have different types of buses inside the computer. The first one I want to discuss now is called address bus. Address bus sends the memory address on which the data is located. Because in the memory inside the computer, we have different addresses, which are simply different places on the memory on which data is stored. So when we want to collect some piece of data, we need to know on which address it is stored. So address bus tells us which address it is. Then we have data bus, which sends the actual data to or from the memory. And the last kind of bus we have is called control bus. Control bus carries commands that come from CPU, or it can carry status messages from other hardware devices. Because, for example, sometimes our keyboard or mouse or any other hardware device that is connected to the computer needs to interrupt this CPU. Each time, for example, you press a key, on your keyboard, the CPU is interrupted to read that the corresponding character. So all these informations are carried using control buses. Here you see an example of a very small control bus which contains only 4 bits. So control buses usually have some bits reserved to show the clock. This clock is used for the computations of the CPU. And there are different flags or different type of data in a bus. For example, here we have a flag that shows reading. When it is set to 0, it means that no data is being read. And we have another flag here, which is write. When it is set to 1, it means that now we are writing data to memory. And this last flag here is for interrupts. When it is set to 1, it means that we have some interrupt from some from some hardware connected to the computer. So in this part of the lecture, we talked about logic gates and how logic circuits can be implemented using logic circuits, and we talked a little bit about logisim and also about buses inside the computers. Please feel free to ask your questions on the forum on Studium, or use the mailing function on Studium to connect the teaching assistants. I will put 2 assignments for this lecture, one compulsory assignment and also one optional assignment, which is about implementing a simple circuit using logisim. And I will provide all the instructions you need to do that. Thank you for your attention.